electron is going to flow from the anode to the cathode. However, there's a depletion region within here, and that prevents the electrons from moving through the diode. And the diode will operate when we put a positive, let's say 0.7 volts across the anode to the cathode, and then that will reduce this barrier depletion region, and then current can flow in the device. So this is our first model of a diode, the ideal diode. And does the ideal diode exist? And the word ideal right away means this is a mathematical device only. Yes.
Will we get a study guide for the exam?
What was it again?
Will we get a study guide for the exam?
Your study guide is the lecture notes, and also you can
do the question.
or this. The notes here indicate as preparation for the midterm, you can solve practice problems located in this location on campus on the modules. And there's also the op-amps, past quizzes and solutions. And then there's practice problems from previous semester tests and quizzes related to the diode. So it's indicating that on Canvas, on the modules, you have there's some problem sessions here related to op-amps and diodes. There's several sessions here with different problems. And then here's some past quizzes and solutions for op-amps. There's multiple versions of different earlier exams. You can open those and basically go through those. And there's let's see, the diodes. And here's a section, recommended practice problems, previous tests and quizzes related to diodes. So there's a group of earlier exam type problems related to diodes. So in terms of study material, there's a lot of material to study right here. Those are your practice type exam problems. Okay. So we have this electronic diode, an ideal electronic switch, and from the way this is drawn, a diode basically turns, an ideal diode turns on when we have 0 volts across it, and instantly becomes a wire, a short circuit. So even there's no other voltage across the ideal diode, because once it turns on, it should turn into a wire. So the current flows from anode to cathode. Whenever the voltage across the diode is greater than 0, the ideal diode becomes a wire, a short circuit. When the voltage across the diode is less than 0, say -1 or so, the diode becomes an open circuit. So this ideal diode is just like your wall switch, basically. It turns on and on instantly. So here, this is the ideal diode. Once it turns on, it instantly has maximum current through it, and it's called forward bias. When it's off, it's called reverse bias. So when the diode is off, it appears as this open switch right here. When the ideal diode is on, it becomes a short circuit or a wire right there. With that introduction, then, we're ready to solve the first. You're ready to solve your first diode, ideal diode problem. So this This is a ideal diode. Has a 1K resistor series with a 10-volt battery. And which terminal is grounded here? Which terminal is grounded?
The negative?
Cathode?
Cathode is grounded. Cathode is the band. So there's the cathode is grounded. So the question is, what's the current through this 1K resistor? Now, how do we get its 10 milliamps?
10 volts divided by, no.
Well, it's 10 volts divided, but why? That doesn't explain why it's 10 milliamps. The idea of diode, if it's on, well, we'll assume it's on. So if it's on, it becomes a wire. And that means that this 1K resistor is connected to ground. And now we have 10 volts across the 1K, and then we can calculate 10 milliamps of current. Now the other circuit, this is the same ideal diode except it's flipped. And why is the current 0 milliamperes?
Can't put a
Diode
ground.
is a short circuit.
It's open.
What is that?
The diode is a short circuit. It's open.
Or open.
Yes.
Why is it
sorry,
open?
it's open.
The ground is at the anode.
You notice the current direction out. And what we're looking for is a contradiction to the state of the diode. So this arrow is saying the current is flowing downward through the diode. What prevents this from happening?
The voltage across the diode would be negative in reference to the.
Reverse voltage.
Yeah. The voltage would be less than zero.
Now you notice here the anode is now grounded. And the cathode is in this direction. The idea of diode only conducts current in the forward direction. So this arrow is implying current is flowing in reverse through this idea of diode, and that's a contradiction right there. So the diode cannot be forward biased in a reverse direction. Why is there 10 volts here? It says the diode has 10 volts across. Why is that?
That's the electric potential from the cathode to the anode.
It's the potential from the cathode to ground. And if this diode is off, that means it becomes an open circuit. So this node here becomes 10 volts. You have 10 volts across, 10 volts, 10 minus or minus 10 volts. So you have 0 volts across this resistor, and that gives 0 current. So you can kind of get the idea that it takes more to confirm the state of a diode rather than just saying it's on or off. You have to basically determine the voltage on the cathode and the anode, determine if there's a contradiction to the assumption that you make, and then a contradiction is the 0 current flowing in a reverse direction right there. So diodes have 3 main states. We have forward conduction, and this drawing here, this is the current through the diode here, and then this is the voltage across the diode. So if we have 0 volts across this diode, the diode will basically, at some point, it will turn on. So this is a practical diode. The practical diode turns on at exactly 0.7 volts. So as we increase the voltage you get to 0.7, it turns on. And this is basically saying for silicon is around 0.7, and for germanium diodes it's around 0.3. Once we get to 0 volts here, the diode turns off. However, if we keep putting a negative voltage across the diode eventually starts to conduct current in inverse direction. And once we put a large enough voltage across the diode in reverse direction, the diode will break down and it will conduct maximum current in the reverse direction. This is typically 100 volts. And this is called the breakdown, reverse breakdown. And it's a useful application because you want that in surge protectors. If you get too much voltage, say from a lightning strike, basically, we have surge protectors that basically they instantly turn on in the reverse, and they short circuit that very high current to ground, basically. And once the voltage vanishes, they return to the forward state again and basically turn on. So, and those are very different diodes from the simple diodes that we've been kind of reviewing here. Those are really very high amperage diodes that can conduct in reverse current, but we need surge protectors. And you can always, whenever your lights flicker during a thunderstorm or something, you share this and probably surge protectors that are opening up to get that current safely to ground. So, forward conduction, and forward conduction is 0.7 volts. However, for calculation, we'll say the diode is, when it's less than 0.5 volts, the diode will be on, and then when it's at 0.7, the diode will conduct. This gets into how do you determine whether a diode is on or on. You'll have to start, you find you're going to have to make some assumptions, and you'll basically want to write down what your assumptions are. So this silicon diode is saying if it volts across is half a volt or less, it's on. If it's greater than a half a volt up to 0.7, it's actually on, but it's not completely on until the voltage gets to 0.7. And we can, this image up here, here the diode is gradually conducting current and gradually turning on, but it technically is not on until it gets to the 0.7, and then basically the current becomes exponential in the diode. Reverse bias mode, this is when we put a negative voltage across the diode. In reverse bias, we can assume the diode is actually off, and there's actually a small current in here. And even though we consider that current as zero, we basically it's called a reverse saturation current. And you have exponentials like e to the minus 30 for that current, but it's still a very small current in the reverse mode. In the reverse breakdown, this is called the avalanche mode. This is where we put a large negative voltage across the diode, and basically it starts to conduct current in the reverse direction because it becomes reverse biased. For a typical diode, that's around 100 volts. And you hitting 100 volts across a simple diode is not an easy event unless you deliberately generate 100 volt DC and then put it across a diode. At one time, there were instruments for testing diodes, and these instruments actually generated hundreds of volts to test diodes. All of that is history now because diodes can be tested by robots a lot more safely than humans actually working with those high voltages. The practical diode, so we covered the ideal diode. This is our practical diode. And if you read this note, it says, this is a model of diode, ideal diode that has a 0.7 volt battery in series with it. So in this model, you assume you have a diode and it has a 0.7 volt battery in it, inside of it, and because of that, when it gets to 0.7 volts across the diode, it instantly turns on maximum current here. Does this device exist?
Yeah. Sure.
So it's implying that we have this diode and it's just laying on the table and it has a 0.7 volt battery inside of it. And logically, it doesn't make sense that that actually is a physical device. Even the battery is very small. So when you use this model, you have to pretend that there's a 0.7 volt battery in the diode. In order for it to conduct, you have to put 0.7 volts across the diode and it conducts. And that's probably the point where you would say, okay, I'll just assume for this diode to conduct in the forward direction, I need 0.7 volts across it. And then I'll just disregard this idea of a 0.7 volt battery in series with it. But this actually explains in circuit laws why this device turns on almost exactly at 0.7 volts. Does the practical diode exist? No. You got two diode models. Ideal does not exist, but practical does not exist. So that means there has to be one diode model that actually exists as a diode. And the reason why we use the ideal and the practical diode basically because it simplifies the circuit analysis with these parts. We can assume a switch is on or off. So that's why we actually use these diodes. Under recommended practice problem from previous semester test and quizzes, maybe there's something before that. It's the diode practice problem. So you can kind of get an idea of what kind of problems can be expected with diodes. So we'll come back to these problems here. This problem here, it has two batteries, 10 volts and minus 10 volts. There's two switching diodes, and it's asking to determine which diodes are on or off. There's another version of the circuit. This version has three diodes. Looks like they're connected in parallel, and the idea is to determine which diodes are on or off. And we notice the instructions for this problem. All three diodes are regular diodes. Use practical models, 0.7 volts if on, and find the current in the voltage. Which diode is on? And show you the justification for the diodes which are on. Always justify your assumption. So problems like that are straightforward, and that's because you're using a diode that doesn't really exist. A real diode is called a real model is called the exact diode model. And this is the equation for the current through this diode. It's I0 e to the V diode over thermal voltage, which is VT minus 1, and that's approximately I0 in this exponential equation. So if you take this equation and plot it, this is the curve. Similar to curve to this you'll get. This is the diode current, and this is the diode voltage here. Now, if you're solving diode current, diode circuit, and each time you solve it, you must use this equation, you're definitely going to have a very complicated, challenging mathematical analysis to work with. So usually the best step is to just assume practical or ideal, and then worst case, you can go back in and solve with this exact model. So here's an exact model example. You have a diode, and you have two diodes, and ID1 and ID2, and you only have the IV curve for one of the diodes. So you bring in a new diode, and it asks you what's the current voltage relationship for the new diode, and the ideal model or the practical model will not solve this question. We have to use the exact model equation. So if a question like this appears on the midterm, where you have two diodes, one diode is known and the other diode is unknown, this is the technique that you use to solve that problem. So you need two equations, these two equations, and then some math here. We take the two equations and we subtract them, and we get V diode 1 minus V diode 2 is the thermal voltage VT, L then of current of diode 1 divided by the current of diode 2. And once you put this in a spreadsheet, you're just solving this formula at the bottom right here. Now the way we solve it is, we probably know one of the diodes, the current voltage relationship, and then we can compute either the diode voltage 1 or the diode voltage 2 because we have two unknowns. If we count this 1, 2, looks like the 4 unknowns. So the idea is that if we have two of them, this equation will allow us to calculate one or the other. So we might have 3 knowns here. But let's go to an example here. So here's an example. If you have a data sheet of a diode at 0.7 volts, the current is a milliamp, and now find the diode voltage at these new currents right here. So a question like this means that the practical model and the ideal model could not be used. We have to go and use the exact model. So let's assume one of the diodes is known to have 0.7 volts across it and 1 milliamp current, and we can solve for the voltage across the diode 1 is 0.7 plus 0.025 element of ID1 over 1. And now we just plug in these different currents right here, and we generate a table. These are the known currents, and these are the calculated diode voltage. You notice only one of them matches up to 0.7 volts. That's this term right here. So once we move off to the 0.7, we have to basically just deal with the other different voltages. You notice 0.758. As the current through the diode increases, the voltage across the diode is actually increasing. So this current here will increase exponentially. And then if we were to plot that, that's a crude Excel plot. The actual curve is smoother. It's actually a smoother curve where it turns on. And this diode here doesn't turn on until around 1 milliamp here. And then basically once it turns on, the current starts to increase do this on a, you can build a simple breadboard and actually calculate or measure these curves. So here's it says it's a puzzle, and we can assume, so it's a group of bulbs, There's a battery here, and then we have switching diodes in the circuit. So we turn on the power, connect the battery up, and we want to determine which of these bulbs are on and which bulbs are off. And keeping in mind that these diodes are deliberately intended to keep parts of the circuit on and parts of the circuit on. So let's assume these are ideal diodes. Right there. So which of the bulbs are on? And we can just say let's just say this is 5 volts.
One, two, and three.
1,
2, and 3.
1, 2, and 3.
Yeah.
What about 4 over here?
There's no current flow,
And why is no current?
because the cathode is connected to the positive side.
Okay, cathode is connected. If lamp 2 turns on, then the cathode will be connected directly to the positive terminal of the 5-volt battery, and then that means current will attempt to flow in reverse to it, so this will basically stop the current. And then lamp 4 should be on. Lamp 1, the cathode is in the right polarity, so this diode can conduct. And then this diode here, if lamp 2 turns on and lamp 3 turns on, then this diode will conduct in the forward direction. So that means that those 3 bulbs will turn on, and then this bulb will turn on. Now, if the battery were flipped, what would happen in the circuit now? The battery polarity was flipped.
Oh.
Would lamp 4 now turn on?
No.
So if the battery would flip, this would become a negative terminal, and then here, and this would be a positive terminal. So this diode here would have a negative on its anode, so it would not conduct so the current would go through here and try to come to this diode. This diode would have a negative on its terminal, and it would not conduct. And now we notice here, this would be a positive voltage here. And then this would be a negative voltage. So would lamp 4 turn on?
No.
So this diode is going to have, now this is a positive terminal here, but is this diode on?
No.
It's not on. So it's kind of a sequencing. When the circuit would start up, lamp 4 would probably blink for a moment, and then once this diode is fully on, then lamp 4 would basically go on. So if you flip the battery, all the bulbs should go on. And it takes a little study to decide if this, that means the plus from the power supply would not get over here. Now, three would not be on, and then you wouldn't get the plus here. So this point here would become a floating node. It's an unknown state, and if you were designing the electronics for this, you would want to avoid unknown states. So if you put the battery, lamp 4, as I said, when you first turn the battery on, it would probably flicker and then go on again. So all the lights would be on. And another circuit, again, assume 5 volts here. So which lamps are on and which lamps are on? And we have to trace the current path and find diodes that will conduct in the forward direction.
One, two, three, four. 1, 2, 3, 4.
One and one and two with flickers. Zero focus there.
Now for the lamp 1 to turn on, it needs a return path to the negative battery terminal. However, diode 2 here, the second diode has this cathode here, so that could block lamp 1 and it might block lamp 2. And then over here, what about lamp 3 and lamp 4?
Three of which are not this.
So lamp 3 and lamp 4, current will attempt to flow in this direction, and then it will attempt to flow in this direction. And then what happens?
It goes down and left.
It was, the voltage would divide.
So we're going to assume these are zero resistant light bulbs, so they don't really form voltage dividers. The current will
The current is
current passes through lamp 3, or attempts to, and basically it can turn and pass through lamp 4. The current needs a return path to the negative battery terminal. So this diode at the lower part, what about this diode?
that just passes through.
That's a return path. So lamp 3 and lamp 4, they have return path. And what about lamp 5?
No.
Lamp 5 is blocked in the reverse direction. And lamp 1 and lamp 2, what happens to those?
They have no return back.
Does lamp 2 have a return path?
No, it's lost.
So the current trying to pass through this diode, it's a forward, looks like a forward path. However, there's no path to actually go to ground, to the negative battery terminal. So what's the summary then? Which lamps are on?
3 and 4.
2 and 4?
3 and 3.
3 and 4. And that's the seriousness of these designs. If your electronics is millions of miles out in space, and then you have the buttons to manipulate it, you definitely want to, and if you come across videos of some of these space devices when they basically unfold themselves. The antennas come out, the arrays come out, the batteries come out. All of that sequencing has to be controlled by switching circuits. So you want to be certain in your design that you're actually designing something that doesn't go into a stalled state. So whatever the purpose here, lamp 5, lamp 2, and lamp 1 was supposed to be off here. Now types of diode. PN junction, the most common type, and then there's also a Zener diode which we'll be studying. This is designed different. Zener diodes can conduct current in both directions, forward and the reverse direction. We'll come to those later. Zener diodes are designed for very specific voltages, and it's called reverse breakdown. So there's a very distinct difference between this PM diode and a Zener diode. Photodiodes, basically. Either LED or LEDs diodes. LEDs are photodiodes are sensors to receive light. And these diodes basically start conducting light when they receive light. And then LED diodes are diodes that actually emit light. And you can get different spectrums of light. There's also photovoltaic diodes. PN junction exposed to a certain wavelength. These diodes can be used as a energy source. And this is just showing the light LED diodes basically. They basically, when the PN junction turns on, they emit some spectrum of light. And you have infrared and other spectrums of light from these diodes. There's also Schottky diodes. These are very fast switching diodes, and they're intended for digital circuits that are switching very fast. And then there's Schottky diodes. These diodes, you can expect these names come off of from the inventors of these particular diodes. So Schottky is a 4-layer diode, and you can, as I said, you can always research these diodes. This could be probably used in high power electronics for different AC switching circuits. But since we're staying with this simple, it's that. Now you can do your own piece-wise analysis of a diode circuit. So here's probably in the eval library you might find a VN, this 4148. This should be a silicon diode, and it's supposed to be a breakdown of 0.7 volts. So if we take your 5-volt battery of 1,000 ohm resistor, and then put your diode in series here, and then make sure we ground this terminal. Now your prediction would say that this diode turns on at 0.7. What kind of diode is this in P-Spice?
Ideal.
Partial. Partly.
What is
Now, the notes say assume this number. But P-Spice disagrees with this number. The notes say assume a silicon diode, you turn on this 0.7 volts, and now when we enter the circuit into P-Spice disagrees with that number. So what's the turn-on voltage of this diode?
5 minus 0.7.
Okay,
677.
677.2 millivolts.
So
Instead of, so which one is right? Is the Pascal model right or P-Spice correct?
P-Spice?
P-Spice is correct. So this is an exact model diode. So it's using an exponential equation to calculate the actual current voltage across this diode. Now you can calculate the error in assuming the diode turns on at 0.7, but if this were, so if this question were given on a exam, basically, it would probably say use the exact model to calculate the voltage and the current through these diodes instead of use a practical. If the question said, what would be the voltage on Vout1 if this were an ideal diode?
0.7. Oh,
So what's the, if this were an ideal diode, what would be the voltage on Vout1?
5 volts.
Which one?
5.
could be 0.
Now, ideal diode, when ideal diode is on, what does it become?
Short.
A wire?
It becomes a wire. So, if this were an ideal diode, then this would become a wire. What would be out?
Oh,
5 times.
So V out now becomes a terminal connected to ground. So V out would basically turn into a short circuit. And so the circuit doesn't really have application with an ideal diode. It only, I mean, if the problem says assume an ideal diode, then of course V out would be equal to 0, but if the question says assume a practical, V out would be 0.7, and if the question asks what is V out 1 with an exact model, that means you've got to go to get that equation and solve it on your calculator. So it's 3 levels of problems here. And it wouldn't be unusual for an exam problem to say solve the problem using all 3 types of diode models. So solving diode circuits. The state of the diode is unknown and might not be intuitive from the schematic. So to solve diode circuit, write down all circuit equations and simplify as much as possible. And many times if a circuit has different resistors and diodes in it, it may not be so simple, but it's what's the circuit equations that have to follow when you're solving diode problems? What's the 3 main circuit equations?
Ohm's law, VC over V.
One starts with an O, what's that one?
Ohm's law
Ohm's law, and 2 start with K.
for cross current law.
Those 3 must be followed if we're solving circuit equations, so we don't have any variations. So this one may not be obvious from the way the schematic is drawn. The next is assume a diode is in one state, it's either on or it's off. And use the diode equation for that state to solve the circuit equation and find I sub B and V sub B. This is what PSpice. PSpice uses the exact diode model. And, so PSpice doesn't have to assume it's on or off. It's just if you were working a problem, you would have to assume it's on or off. Check the inequality associated with that state. That means the range of validity. If the diode current or the diode voltage satisfy the inequality, the assumption is correct. If it doesn't, go back to step 2 and start with the other state. So if we assume the diode is on and we get a contradiction, that means we have to go back and resolve the problem and come up with a result. Now the lower part here, for complicated circuits, use diode circuit models. And this is where it's in PSpice, it's always going to use the exact model. So we'll, as we move more into diodes, it wouldn't be unusual to expect the exact model on the midterm. The midterm could have 5 or 6 questions on it, and you have an hour and 15 minutes to complete those questions. So the idea of those questions is that they're not questions that you're going to get stuck on, basically. Because if you get stuck on them, you're basically going to use up your time. The way you, if it's 5 questions, how long should you spend on each problem?
15 minutes.
You have an hour and 15 minutes, and you got 5 questions.
Yeah, 15 minutes.
You probably want to aim for something like 7 or 8 minutes for each question. And that's going to leave a relief time to basically go back through the problems that you basically have already covered. When you solve these electronic problems, scan through the whole document first. So you try to solve what appears to be the easiest problem first. That's something you have to do. Usually the easier problems have less weight compared to the more complicated problems, so that you don't have to kind of decide on that yourself. All right, we'll complete the diode models next time, and then we'll move into diodes and DC circuits. All right, that's it.